So here we're going to look at how an angle relates to sides of a triangle as they change. And so in this particular problem we have someone's reeling in a fish, and the end of the fishing pole is 11 feet above the water. So this horizontal line here is the water, and regardless of where the fish is, as the fish moves in, right, as the fish moves in, you can see that, for example, if the fish is here, the triangle is going to change except for this side and the right angle. Okay, so the right angle and the side of 11 will not be changing. Okay, now we need to identify the things that are changing with time that are relevant in this problem. A fish is reeled in at a rate of 0.7 feet per second. Well, that's this distance here. That's the fishing line at which you're reeling it in. So let's label that X because I know that's changing with time. And then it says, at what rate is the angle between the line and the water changing? So of course that's this angle, so we'll call that angle theta. So those are the two things changing with time that are relevant in this problem. Also notice that we're told that there's 25 feet of line out. That's a specific moment, right? Because that's at a specific moment X will be 25. So maybe we could actually start working on that as well. At this specific moment we have a right angle, we have 11, that never changes, but now this is 25. Can we figure out the specific angle at that point? Well, sure we can. It would be, since in relation to this angle I have opposite and hypotenuse, this angle will be the inverse sine, the arc sine of the opposite over the hypotenuse. And making sure we're in degree mode, actually, rather than approximate this, I'll just leave this as my angle so that I can plug that directly into any calculations I may need, if I need that in fact. Something else we know at the specific moment is the fish is reeled in at a rate of 0.7 feet per second. So that's how fast the fishing line is moving. So that's dx dt is 0.7 feet per second. And again, my units are all consistent here. Feet for length and seconds for time. And so I'm not going to put my units in my labels here. Now, x, however, is getting smaller, right? So that is a negative rate of change because x is shrinking. So that's important. Now let's try to set up our equation, our relationship between x theta and 11. And we've already seen it down here, right? We know that the sine of theta is the opposite side over the hypotenuse. And now we need to differentiate this with respect to time so that we have our rates in this equation. So I differentiate both sides with respect to time. Theta and x are both functions of time. So what we end up with is the derivative of sine is cosine of the same angle, but by the chain rule I multiply by d theta dt, since theta is a function of time. On the right side, this is the same thing as 11x to the negative first. So when I differentiate that, I get negative 11x to the negative second times the derivative of x, so dx dt. And now I plug in any values that I know. So I look at my specific moment and I try to plug things in. So, for example, x here is 25. So I know I will be plugging in 25 for x. I know dx dt is negative 0.7. And we're looking for the rate of change of the angle, so that's what we don't know. And then we need theta or the cosine of theta. So we know theta is this, right? At that specific moment. So I could plug that in. I could write cosine of this angle. And, you know, I could put that in my calculator and work with it. However, so that would work. That would be fine. But it'd be easier. I can already tell that at this specific moment, rather than plugging theta in, I know the cosine of theta. Cosine of theta is adjacent over hypotenuse. So if I knew this side, which I could get by if I knew the adjacent side, I could just plug the adjacent over hypotenuse in for the cosine. Well, the adjacent side would be calculated using the Pythagorean theorem. Squaring this, I get 625 minus 121. I believe is 504. Let me double check that real quick. And yes, that appears to be right. So now for the cosine of theta, I can plug in adjacent over hypotenuse, which is square root of 504 over 25. So I have that times our unknown d theta dt equals negative 11. 25 to the negative second means square the 25 but put it on the bottom, so that'd be over 625 times negative 0.7. So d theta dt, all I have to do is divide both sides by this fraction or multiply by the reciprocal, so that's what I'll do. 11 times 0.7 is 7.7, and negative times negative is positive, over 625, so that's the right side, but I multiply that by this reciprocal, 25 over the square root of 504. And notice that I haven't rounded anything in this yet. Okay, so my rounding is going to happen here at the very end. D theta dt is going to be, when I multiply this out, I get a positive 0.0137. Now what unit would this be in? And we have to be careful here. Degrees will never come out of numeric calculations. In fact, radians will. So this is actually radians per, and the time here is in seconds, okay? So what we have to do now to make, well, we don't have to, but it would make sense to convert this to degrees so that we can understand what this is saying. So to convert this to degrees, we multiply 0.0137 radians by 180 degrees over pi radians, this conversion factor. 180 degrees equals pi radians. So 0.0137 times 180 is approximately, I'm rounding here, approximately 2.5 degrees per second. So that's how fast our angle is changing. And it's a positive number, so our angle should be increasing as the fish gets closer. And we can see here, when the fish is closer, this angle is bigger than what it was before. So that answer seems to make sense. So there's an example of related rates using trigonometry and angles.